Welcome everyone to Intel's Chalk Talk series. Over the course of the next couple of months, we'll be hitting on some key topics across Intel's portfolio to provide additional context around our strategy and how we're approaching customer problems each and every day. Today, our focus is on acceleration, the portfolio that we have within that, and the strategy that is behind that, the acceleration portfolio. The intent of today is not so much to present at you and talk about speeds and feeds of our products, but really about the why and the how for how we approach solving customer problems with those solutions. Today, I'm joined by four of Intel's top leaders to discuss with you. We've got Sailesh Kottapalli, we've got Kavitha Prasad, Sachin Katti, and on virtual, we have Jeff McVeigh as well. So with that, I want to pass it off to Sailesh to start with the presentation.
All right, thanks, Jordan. Glad to be here. So our goal for Xeon, the way we think about it is it is the predominant general purpose processor in the data center. Essentially, it spans a wide gamut from all kinds of compute, network, and storage usages, as well as the scale all the way from a small-scale monolithic server all the way to data center scale elastic infrastructure solutions. The one thing that's we see is that the data center landscape continues to evolve across different kinds of workloads, usage models, as well as the deployment models. In all of this, the one constant that we see is the ever-increasing need for general-purpose computing that is delivered with the highest levels of efficiency and sustainability. So when we look at Xeon, our architecture philosophy is that we want to deliver consistent performance with high degree of elasticity and utilization across all kinds of usages, including single-tenant and multi-tenant usages. In Sapphire Rapids, we architected the processor to make sure that it can deliver a significant performance out of the box. When I talk about out of the box, it essentially means that performance with existing architecture contracts. So whoever the workloads and usages that people were running on the prior generation, you just drop them into this box, you get massive amounts of performance uplift. In addition, one of the major focus in Sapphire Rapids was to make sure that we look at some of these growing and emerging usages and identify the predominant functions that are at the center of all of those and build architecture capabilities that actually provide multifold improvements in some of those emerging usages. And we did that using both instruction set architecture acceleration capabilities, as well as dedicated engines. And as we were architecting this, one of the key things that we did is to make sure that we approached it from a software-first approach, to make sure that we architect in a way that it enables for easy software use, as well as ease of integrating that into our existing infrastructure. And as we did that, we wanted to make sure that the software architecture actually spans across the entirety of the compute engines and different kinds of XPUs that you see in the data center, so that it actually works well with GPUs, ASICs, and FPGAs, and so on. So let me talk about a few examples of these acceleration capabilities in Sapphire Rapids. One of the exclusive areas of focus in Sapphire Rapids was AI. We see an increased adoption of AI in better decision making across all kinds of business logic and usages that people use in the data center. And so we see AI as becoming ubiquitous. And what we wanted to make sure is that in all of the general purpose infrastructure that people deploy, as they actually need to integrate AI capabilities, they get optimal performance on the general purpose infrastructure that Xeon is usually at the center of, right? So our view is that we want to make sure that we offer the best dedicated solutions for AI, as well as the best general purpose solutions that deliver good AI performance. And that actually is critical to make sure that we have the right data center elasticity for a very ubiquitous use of AI. So one of the things we architected in Sapphire Rapids was the Amx Capabilities, which is the advanced matrix extension. These massively speed up some of the tensor operations, which are at the heart of most of the deep learning solutions. So in Sapphire Rapids, what you'll be able to see is that you can actually do 2,000 or 2K operations per cycle of int8 data type and about 1K of bfloat16 data type. And these are all will bring in a significant amount of AI performance acceleration. And when combined with the general purpose strengths, large caches, memory capacity, and high memory bandwidth, including some of the Sapphire plus HBM variants, what we see is that Sapphire Rapids will deliver a significant performance improvements across inference and training. Another example of that is that when you look at data center usages, there is a significant amount of overhead in terms of data movement functions that happen. So one of the things that we architected is really optimal data movement engine that we call data streaming accelerator that actually helps offload and actually speed up a lot of the common data movement operations that you see in the data center across CPU caches and memory, as well as from the CPU to I/O, including storage and network. And what we see is essentially a multi-fold speed up in some of these functions, which actually help the overall workload performance. But not only that, it actually helps lower the CPU utilization, helping it to be used for other functions in parallel while some of these engines are taking care of the data movement, and actually deliver an overall better and deterministic performance. Yet another example that we've talked about is really around what we call the Qat engine. If you look at the data center, pretty much all the data in the data center is cryptographically protected during storage or transmission and in use. And so that's something that's becoming a default, and we wanted to make sure that we provide the right crypto acceleration in our processor. In addition, we also see that as the data sets continue to grow, that data will continue to be maintained in a compressed format, and we wanted to make sure that we have the right engines to actually provide the best compression and decompression speeds. So QAD provides that. What we see is that with the latest generation of QAD that we've actually integrated into Sapphire Rapids, on some of the most popular crypto and compression algorithms, we see an order of magnitude speed up. So the main focus for Xeon has been to look at some of the most common things that we see are becoming ubiquitous or important, and we speed them up either through ISA or through the dedicated engines. And I think you will see that significant improvements with Sapphire Rapids. With that, let me turn over to Kavitha to talk about AI more broadly.
Thank you so much, Sailesh. When you look at AI broadly, you can broadly classify it into 4 modalities. One is the traditional machine learning. It could be like the classification, regression, k-means, etc. Or it could be probabilistic methods like Bayesian models. Or the third is the deep learning, which is gaining popularity right now. That's the CNNs, transformer models, GNNs, etc. And the fourth one being the domain-specific AI, like the biology or physics or tokenomics, for example. And when you look at the applications that are deployed, most of these applications make use of, if not more than two to 3 to 4 modalities to gain meaningful business outcome. For example, digital twins falls at the intersection of all these 4 modalities. Autonomous systems falls at the intersection of all these 4 modalities too. And when you look at the compute requirement of these 4 modalities, it could be scalar compute, it could be vector compute, it could be spatial compute, or it could be matrix compute. So in that context, the AI compute requirements are very heterogeneous. But if you look at the use cases that the customers are deploying, and most of the developers are actually software developers or subject matter experts. They need to gain the performance out of all these heterogeneous compute right out of the box. So software becomes the key. The software needs to be the homogenizing factor across all these different hardware components. And if you look at the industry today, x86 is the largest software ecosystem that is available. And no doubt, it's very popular when deploying these AI inference models. And the third critical thing is to deploy AI, you cannot look at it as deploying for one or two bespoke use cases. Today, the analyst reports suggest that 60 to 70% of businesses are actually investing in AI, but only 20% of those investments are actually resulting in meaningful business outcomes. So what is Intel doing to address this so that AI can be deployed more broadly in the industry? Let's take two examples. One is the traditional machine learning modality. In that case, the entire ML process today can run on Intel Xeon Scalable processors. With AVX512 that has been incorporated in it natively, Xeon can generate 1.5x greater performance than other CPUs over 20 plus common benchmarks out there. And also, Intel's distribution of modem results in 90x% improvement on Panda's acceleration. Or Intel's distribution of scikit-learn actually gets 38x performance right out of the box for machine learning use cases. And now let's look at the deep learning modality. When you look at the deep learning inference, the Intel DL Boost enables customers to get end-to-end performance out of the Intel Xeon processors. And with AVX512, we are able to combine 3 instructions into one, and that combined along with DL Boost gets the performance the customers need right out of the box for the embedded AI applications. And now when we look at the deep learning training, Intel has Habana Gaudi accelerators for those deep, high-density deep learning training. Habana Gaudi is actually one of the accelerators that has been enabled on AWS DL1 instances. It is the only accelerator that's vendor provided that's actually enabled other than GPUs. And then, like I mentioned earlier, AI is not just about the heterogeneous compute that's available, but it's about the software ease of use that defines the development to the deployment times. So when in that context, if you look at the OpenVINO toolkit that Intel has, customers can write once and deploy anywhere. In fact, OpenVINO backend is available even as in TensorRT by NVIDIA. Intel AI Analytics Toolkits enables customers to get end-to-end data science and analytics pipeline working right out of the box and provide the efficiency and performance that they need. And 1DNN optimizations have been up-leveled into TensorFlow 2.9 so the customers can use it right out of the box. And when we look at the 4th gen Intel Scalable Xeon processors, we have Intel AMX, like Sailesh mentioned, which gives the next gen DL boost to the customers. This helps accelerating deep mathematical computations so the customers can get the benefits right out of the box. Now let's look at a few of the customer applications that gain the benefit out of what Intel has to provide. One of the examples is VBank. This is a banking, customer where they need a lot of data from all these different customers to provide meaningful AI results. But the key thing here is that these data that comes from customers is highly sensitive and needs to have security and privacy so that it is used meaningfully. In that context, Intel was able to boost the performance by using the cryptography library, where we were able to incorporate partial homomorphic encryption with federated learning so the customers could get benefit right out of the box. The key with Intel solutions, both from a hardware perspective and the software perspective, is faster response time, improved performance, and greater computing power. With this, I will pass it on to Sachin, who's going to talk about edge acceleration.
Thank you, Kavitha. So really excited to talk to you all today. I'm CTO for Network and Edge, but another hat that I wear is I'm the technical chair for the Open RAN Alliance, and really excited to see many of the features that are coming here to accelerate the transition to Open RAN for telecommunications networks around the world. So I want to take a step back. Networking has been going through a decade-long transformation on becoming software-defined. So if you just wind the clock back 10 years ago, we were used to having our networking infrastructure, whether it is LTE infrastructure or any of the common traditional enterprise networking, being fixed function appliances. And Intel has powered the transformation of these fixed function appliances into general purpose platforms where networking is running as a piece of software on top of these general purpose platforms. And customers love this because they can actually get much more agility into their infrastructure. They can deliver new services, new networking and security services at much faster speeds because it's now software rather than a hardware upgrade like it was in the past. But one of the challenges when you do such transformation is that you're used to hardwired acceleration for many of these capabilities in the past with these hardware, with these silos that you had in the past. But when you move towards these general purpose platforms, how do you get the performance you need for many of these demanding networking and security applications while getting the flexibility of software, especially with the advent of cloud-native technologies in building many of these networking software. So that's really the goal in building many of these acceleration technologies into the Sapphire Rapids platform, and as well as previous generation platforms that we have already successfully shown how to. So our customers are using these to deliver agile network infrastructure for packet and signal processing, for load balancing, and so on. This has transformed telco operators around the world, as well as enterprise networking applications around the world. So I want to kind of walk you through what are the capabilities that we are bringing to the table here with the lens of three very important use cases that you all are experiencing and using, and you don't probably, it works so well that it actually becomes invisible in terms of infrastructure. So I want to talk about 5G, and there are two basically use cases that we accelerate. So one is the 5G core. So this is the core of the 5G network. So if you're connecting to an AT&T network or a Verizon network, the core of the network that's actually routing your traffic to the internet, it has to do a lot of work. It has to do a lot of packet processing. It has to make sure that your communication is secure, that your personally identifying information is handled securely, all while giving you the speed and the latency that you have come to expect from these networks. So Intel has been working on accelerating the 5G core, starting actually with LTE with 4G core, but now with 5G core increasingly being deployed around the world, providing acceleration for many of the common design patterns in these workloads to make sure that you get a great experience as a user. So in the previous generation, with Intel's platforms, we showed that you could get a 42% improvement in the 5G user processing function. And this really is the guts of that 5G core. It's the one that's handling all your traffic. But what's really underneath this thing? So in 5G core, you really are handling traffic. So you're doing a lot of packet processing. Like Sailesh was mentioning, you're doing a lot of crypto. You're encrypting and decrypting packets, and you're trying to do this at line rate at several gigabits per second. And you need the capability to handle that. And you're handling a lot of personally identifying information. So you need the security capabilities to handle that in a good manner. And this is where Intel's capabilities are on deep learning boost. So this is giving you new floating point 16 instructions as well as VNNI instructions that allow you to run modern AI inference and training workloads as part of this 5G core and accelerate performance. Similarly, we are introducing crypto capabilities that can offload all of the encryption and decryption work from the cores and almost do the work of 1,000 cores as part of this acceleration. And SGX is allowing you to handle all of this information securely. In addition, we are adding DSA, so the data streaming accelerator. This is really accelerating data movement. 5G core has a lot of data movement that happens in the user plane and the control plane, and that acceleration significantly improves the performance of the 5G core. And finally, DLB, which is the dynamic load balancer. This is allowing you to balance load and balance traffic across a bunch of machines to make sure that everyone gets a consistent, great user experience. So that's on the 5G core. Now, as I shift towards the edge, you start talking about the cellular radio access network, or vRAN. And this is going through a rapid transformation. So this is a big part of our infrastructure. We all rely on it to get constantly connected, for us to be able to make phone calls and get internet connectivity on our phones. And this is going through a transformation where instead of fixed function appliances, it is becoming a general purpose platform on top of which you will deploy these networks. So on this one, we showed even in the previous generation a 62% performance gain compared to the prior generation. And this, again, if you think about what is underneath this workload, it's a mix of packet processing, signal processing, and bit processing. And we are providing acceleration for each of these. So for encryption and crypto, we are providing QAT capabilities to accelerate the packet processing. For signal processing instructions and bit processing instructions, we are providing AVX 512 instructions to be able to accelerate and provide great performance. And finally, with the new Sapphire Rapids introduction, we are adding two really good capabilities. So one is around 5G specific instructions that are taking specific parts of the 5G workload, for the 5G RAN workload, and providing accelerated performance for this right in the CPU core itself. And in addition, we are taking what's called FEC. So this is the error correcting codes that consume a lot of compute horsepower. We are adding on-die acceleration so that you can run these kinds of functions at much faster speeds and be able to deliver these kinds of vRAN solutions. So what does this matter to the customer? Really, what this generation is going to show is that it's now possible to run what's called massive MIMO with 64T and 64R. What that really means is you have 64 transmit antennas and 64 receive antennas, and those provide an immense speed boost for your 5G phones. And those kinds of very demanding latency-sensitive software can now be run on these general-purpose platforms. The last one, much closer to the enterprise world, is SASE, right? So this stands for Secure Access Service Edge. If you are an employee, you are probably already using this. You need it to get access to your enterprise-sensitive data and applications. And this is going to be a mix of crypto, because a lot of your traffic has to be encrypted. This is a mix of SGX, because your data needs to be protected. And this also needs capabilities like DL Boost, because it's doing a lot of security scanning applications like Hyperscan. So this is leveraging AVX 512 and DL Boost capabilities in Sapphire Rapids to accelerate the performance of these SASE applications. So this is already taking off. This slide, as you can see, is showing the proliferation of such software-defined networking architectures around the world. And this is specifically focused on the vRAN part. If you now are looking at a commercially deployed vRAN, if an operator is talking about a commercially deployed vRAN, it's running on Intel. There is no other choice today for anyone to be able to scalably run this demanding application. And this has been the great work that Intel has been doing for the last 10 years in showing the world that it's actually possible to run a 5G radio access network as a piece of software on a general purpose platform. And the real benefit of this is now you're able to bring cloud native like automation capabilities to the telecommunications world and bring that same agility and automation benefits to the telecommunications world, which historically has been lacking. So I want to take two specific examples and talk about customer success stories. So one is with Vodafone. This is a fixed network provider, and what that means is it's providing your broadband access to your home. And one of the problems they were facing was, how do I make sure that I give differentiated performance depending on what the application needs? So previously, they had to match a subscriber session to a static setting. Instead, we wanted them to be able to dynamically route traffic based on what kind of quality of service they wanted to deliver. So we worked with them and the Berlin Institute to basically show how they can build a cloud-native implementation of their fixed network service, and that gives them the agility and flexibility to route traffic to the right place to deliver the right quality of service to those subscribers. So that's one. The second one, much more familiar with the US audience here perhaps, is Dish. This is aiming to be the fourth cellular network in the US. And interestingly, and it's a revolutionary approach because they are now completely designing their network on an open software-defined manner rather than having any legacy infrastructure. And they turn to us as to how can they actually cost-effectively build such an open RAN-enabled network. And we worked with them in figuring out how they can take our FlexRAN software, our platforms for vRAN, and design in solutions where they can provide a 40% reduction in cost over traditional solutions that they were previously taking on. And this is really a first demonstration of an ORAN and an open RAN-based networks being deployed at scale 5G, starting from 5G from day zero, and being able to deliver at a scale like the entire country of US. So a lot of transformation happening, software-defined networking transformation happening because of the capabilities, acceleration capabilities that are coming in these platforms. So with that, I'm going to hand it off to Jeff to talk about HPC. Jeff, over to you.
Great, thank you so much. Great to be here with everybody. Now, high-performance computing is all about computing at the highest levels. And why do we do this? We really need to focus on solving the world's most difficult challenges and doing it faster. But how? How do we make that happen? We do so by making sure that our processors and each core is working smarter via the built-in accelerators that we've been discussing here today. Intel's AVX 512, as well as the Intel DL Boost, are purpose-built accelerators that advance HPC workloads that require the most high-demand performance for both AI and math processing. AVX 512, for example, helps us schedule the logic to keep the data pipeline completely full as we're processing those workloads. We're able to achieve significantly higher throughput compared to implementations that just have AVX2. Now let's explore a few critical use cases that are enabled by AVX 512. The first is around simulation and modeling that are used in computer-aided engineering, which is important for developing new products that perform better, such as more aerodynamic cars or the discovery of new vaccines. Intel's third generation Xeon Scalable processors achieve up to 18% higher LIMPAC performance and 32% higher Reliant performance compared to the competition. Moving on to financial services, another major category where we are seeing a blend of traditional HPC codes and techniques with new AI methodologies. This is really where the combination of AVX 512 plus DL Boost provide major benefits. On FSI codes like derivative pricing and X-value adjustment portfolio calculations for risk modeling, we see the third generation scalable processor providing up to 50% higher Monte Carlo performance with the AVX 512 that's built in than the competition's AVX2 implementation. Now, finally, in life sciences and genomics, these really require the most performant HPC systems. AVX 512 again provides higher performance for those applications in life sciences to increase the scope as well as getting shorter time to result for those data-driven research. Compared to prior generations, the third gen Intel's Xeon Scalable processor can deliver 1.6x higher geomean life and material sciences performance, as well as 27% higher performance on the NAMD molecular dynamics code than the competition. These are meaningful, substantial improvements for getting those results much faster for those critical solutions that we need. Now, the next slide, please. It's critical that software ties all this together. The silicon by itself doesn't bring that to life. It's the combination of the hardware and software together. And it's really important to be utilizing open cross-platform tools, libraries, and capabilities to leverage both the developer investment and time to optimize those HPC codes for their systems. The One API platform provides that unified programming model that can seamlessly tie together both CPU integrated as well as discrete accelerators. The accelerators that I've been talking around, AVX 512, are exposed through common programming interfaces and libraries such as the One MKL or Math Kernel library, as well as the data analytics libraries and compilers that are found in the One API toolkits. Now let's look forward to the future. Our fourth generation Intel Xeon Scalable processor, codenamed Sapphire Rapids, will include substantially new capabilities like Intel Q8T, providing higher gigabytes per second and ops per second for storing and accessing huge amounts of data that are used in HPC applications. The Intel Data Streaming Accelerator speeds data copying and transformation. An example of how this is applied is in the Intel MPI implementation, where DSI is used to accelerate point-to-point communication, as well as the Intel AMX will deliver AI-infused HPC workloads at a substantially improved performance. Including in our Sapphire portfolio will be variations that include high bandwidth memory. This is a case where Intel is the first to integrate HBM into an x86 CPU package. This provides massive benefits in terms of performance, TCO, for faster speeds and reduced needs, especially compared to systems with only DDR performance. This is critical for those workloads in the HPC space that are bound by accessing memory. Bringing in that memory and integrating that directly allows for that performance benefit. In addition to our roadmap for our CPU accelerators, we have a rich set of discrete accelerators as well. Just this morning, we announced the new Intel Flex Series GPUs that are really addressing what I call HPC on the edge, lower power envelope, accelerating inference, as well as other capabilities, media delivery, cloud gaming, VDI, and others. These will be followed by our flagship GPU, codenamed Ponte Vecchio, and then the Rialto Bridge GPU. Now, let's explore, if we can go to the next slide, a few customer success stories that illustrate the value in the HPC domain. CERN, for example, has the world's largest particle accelerator. They had a desire to use inferencing to get faster results than traditional Monte Carlo-based simulations. Researchers used the Intel AI Analytics Toolkit to simulate a collimator using a GAN model. This required only a fraction of the compute of previous methods utilizing those built-in accelerators that are exposed through the software of one API. In addition, Argonne National Labs is at the forefront of delivering the exascale computing capabilities necessary to address some of the world's most complex problems in science and engineering. The Aurora Supercomputer is targeted to deliver over 2 exaflops of peak of performance when it's deployed. Each node in Aurora includes 2 Sapphire Rapids with HBM plus 6 Ponte Vecchio GPUs. All of this is tied together with the common programming model of one API. This system will help to deliver safe and clean fusion reactors, neuroscience research, and more effective treatments for cancer, just to name a few applications. Aurora will help to deliver and bring in a new era of science where compute-intensive scientific endeavors previously thought impossible will become reality. And with that, let me hand it back to Jordan and the panel.
Awesome. Thank you so much, Jeff, and thank you to Sailesh, Kavitha, and Sachin as well for the great presentation.